All right, Chapter 10, Section 5, Angle Relationships in Circles. Just as the title suggests, we're going to be talking about how an angle can interact or intersect with the circle. And there's really kind of three different ways that can happen. Three different ways that can happen that we're going to pay attention to at least. It is possible for an angle to exist completely separated from a circle, obviously, where it just completely misses it. There's no intersection points at all, in which case that's a very boring case where there's nothing about the circle that would tell me anything about the angle because there's no intersection points at that point. So we're going to focus on the ones that have something interesting going on. And there are three different ways that an angle can intersect with the circle. And that's what I have here at the bottom of the page that's shown right now, is those three different scenarios. Scenario 1. This is one we've actually already talked about in Section 4. It's called an inscribed angle. If the angle itself, the vertex, the corner of that angle, is located on the circle itself, that's called an inscribed angle. But the first theorem we're going to talk about at the top here, I'm beginning with this because I want to talk about the three scenarios, but the first theorem we're going to circle back to up here is another version of an inscribed angle, because as you can see, that angle is still on the circle. It's just kind of a unique case where one of the sides of the angle extends beyond the circle. Okay, so we'll revisit that in a second, but this is one of the three scenarios where I can have an angle interacting or intersecting with the circle, where the angle itself is on the circle. Scenario 2, the angle is somewhere inside the circle, right? Basically creating this X shape or T shape, however you want to think about it. Somewhere inside the circle is the intersection that makes an angle. Fundamentally, in this case, I create, anytime I have two lines intersecting, I create four different angles, one at each of these parts of the X, okay? And so this is going to also be referencing vertical angles. Hopefully you remember this theorem from previous math classes, but anytime I have two lines intersecting, vertical angles are angles that are opposite each other in this intersection. So left, right, or up, down. Those angles are going to be forced to be congruent. So that will pop up here a couple times in the section. But again, scenario number 2, if the angle is not on the circle itself, it's possible that it just shifted somewhere inside of the circle. And then scenario number 3, I did not do a very good job of kind of showing you what that would look like. This is a very, very extreme case where you notice the intersection is outside of the circle. It's just very, very close. I should have emphasized it more, I think, just to kind of get the point across. But in any case, the third kind of scenario we're going to focus on is, all right, well, what happens if the angle occurs outside of the circle? And in each of these cases, the way I can solve for the angle measurement that is created with these angles, it has its own formula for how to solve it, but they're all very, very similar. In fact, this first scenario, if the angle is on the circle, we've actually already covered how to solve for that angle. This is where I'll redirect you back to Section 4 on inscribed angles. An inscribed angle, again, is anytime I have the vertex of that angle on the circle itself. It can be anywhere on that circle. So in this case, the inscribed angle is basically the Pac-Man mouth that's created with that angle on the circle. And this inscribed angle has what we call an intercepted arc. Okay, basically the arc that's contained within that wedge on the opposite side. And so what we learned in Section 4 is that the measurement of this angle right here is going to be exactly 1/2 of the intercepted arc measurement. So in Section 4, if I knew that this arc measure, say, for instance, was 70 degrees out of the 360-degree circle, if I knew that this arc was 70 degrees, I would know that its inscribed angle would have to be exactly half of that, or 35 degrees. Or vice versa, maybe I knew the inscribed angle measurement. Maybe I knew this guy here was 25 degrees, in which case I would multiply it by 2 to find the intercepted arc measure. In that case, that'd be 25 times 2, or 50. Okay, so it's a very simple computation. There's nothing terribly difficult about the algebra there. And it's really just a one-step problem, but that's what the focus of Section 4 was. Okay, so the angle could be on the circle, inside of the circle, or outside of the circle. Okay, and so we're just seeing these different scenarios, and we're going to look and analyze at these different formulas, the ways to solve for angle measurement in each case. They're going to all look very, very close to each other. So let's start with this case right here, the angle being on the circle itself. Again, Section 4 focused entirely on this, inscribed angles. So this first theorem here is just a very specific set of this. Okay, you'll notice that the angle is still on the circle. But what's slightly different in this case is that one of the sides of the angle, one of the sides of the wedge or the Pac-Man mouth, whatever you think of it as, is tangent to the circle. In other words, it only touches at that one point where the angle exists on the circle, and then it just never touches the circle again. Okay? And here's the good news. Nothing changes about the formula. It's still, if this angle measurement here, see this wedge right here, it's still an inscribed angle. Why is it still an inscribed angle? Because the vertex of that angle is still on the circle. So whatever angle measurement this is, it's going to be exactly 1/2 of the intercepted arc. The difference here is that the arc just happens to continue all the way down to the vertex of the angle itself. But it's still an inscribed angle because the angle is on the circle. And fundamentally, in this case, I end up with two different angles. These are both supplements of each other because this tangent is a straight line. So if this angle right here happened to measure, say, 70 degrees, I just figure out what's left over here. That'd be 110 degrees to make that 180 degree straight line. But in either case, whether I'm solving for angle 2 or angle 1, you'll notice that in either case, the formula is really just the same. It's 1/2 of the intercepted arc. For angle 2 here, it's just what we would call a major arc because it's the majority of the circle. Okay, but it's still going to be 1/2 of that measure. So for instance, if I knew that arc ACB, this major arc right here, was say 220 degrees, I would simply cut that value in half to find this inscribed angle measure for angle 2, and that would be 220 divided by 2, or 110. Vice versa, to look at the flip side of the coin, maybe I knew this arc measure for minor arc AB was the leftover of that 200 of the 360 degree circle. In that case, it would be 140 degrees. So maybe I knew arc AB was 140 degrees. So I could cut that in half to figure out that angle 1 here, the inscribed angle, the angle that's on the circle itself, is 1/2 of 140, or 70. Okay. Again, still that was the focus of section 4. The only thing that changed here with how it looks is that instead of the angle looking a little bit like this guy where the angle is completely contained within the circle, it's just like I took that one side and just rotated it a bit so that it went tangent to the circle at a different point. Angle is still on the circle. Formula is still going to be the same exact thing, where the inscribed angle is 1/2 of the arc measure. A quick one-step solution to find that value. Okay, so now let's talk about these two other ones. What happens if that angle is not on the circle itself? Let's look at first this one. What happens if the angle is inside the circle? You're going to notice that the formula for this is going to be similar. You're going to see some similarities, but you're going to see some differences as well. All right. Here's our angles inside of the circle theorem. How do I solve for an angle measurement if instead of being on the circle, it's somehow moved inside? And so you'll see diagrams like this, and it'll look a little bit like, again, just like an X somewhere on the inside of a circle, an hourglass, or a black widow symbol, whatever you think of it as. Okay, but we end up with this scenario. The angle is quite obviously on the inside of the circle. It's like a very, very, very poorly sliced pizza right in here in this case. In either case, what I end up with here is, technically speaking, I have 4 different angles that are created, right? And for any of those angles, I'm going to be using these kinds of formulas. So the fact that I only designated angle 1 right here and angle 2 right here, technically speaking, I could solve for this angle as well, or that angle that have been unnamed. Okay, that's still possible here. It just would end up being the same as each of their counterparts. So for instance, angle 1 right here would have the same exact solution, same exact result as this angle on the opposite side of it. Why? Because vertical angles fundamentally have to be congruent. So if this guy ended up measuring in at, say, 55 degrees, directly opposite on the other side here, that would also have to be 55 degrees. All right, so that's the vertical angles theorem. Anytime I have 2 lines or segments that cross each other, vertical angles or angles that are opposite each other need to be congruent. If angle 2 here measured in at, say, 120 degrees, this angle on the opposite side of it would also have to measure 120 degrees. So in either case, I can end up solving for all 4 of these angles on the inside. All right, so what about the theorem itself? How do I go about solving? Well, you'll notice, for instance, let's focus here on angle 1. The actual process, depending on which angle I'm solving for, is the exact same. It's just a matter of which arcs I'm analyzing. So let's look at angle 1 right here. Angle 1 right here on the right. You'll notice that to solve for angle 1, it starts the same exact way for an inscribed angle. I'm going to take 1/2 of something. Now, had this angle been on the circle itself, I'd only be taking 1/2 of the intercepted arc. Now, here's where it changes a bit. I still have an intercepted arc right here, arc CD, across from angle 1. But because the angle has moved inside of the circle, you'll notice directly opposite arc CD is arc AB over here on the left. That arc is also technically an intercepted arc for angle 1. It's just behind it. And so how do I go about solving for the measurement of angle 1? Well, I'm still taking half of an intercepted arc, but what I'm doing here is I'm adding up both of those arcs together. AB, the small arc behind it, and then DC, what we would traditionally think of as the intercepted arc for that angle, where the wedge goes. Basically, mathematically, what's happening in this case, if you want to write it off in the margin here, this isn't necessary to like name it this way, but if you want to know what mathematically is happening, we're basically taking an average. If I add two things together and then divide by 2, I've taken an average of the two things. For instance, if I scored a 65 on a test, and then I scored a 78 on another test, if I want to know what my average test score was, I'd add those two test scores together and divide by the number of tests I took. Okay? The same thing's happening here. I have two intercepted arcs, one on either side, and if I was dealing with angle 2, you see it written out here. For angle 2, it's the same thing. There's my intercepted arc, but directly behind it, there's another arc. I'm taking the average arc length between those two. So I'd add them both together, whatever their measurements were in degrees, and then simply divide by 2. Okay, so for instance, if I knew that arc CD here was, say, 60 degrees, and then arc AB behind it was, say, 40 degrees, I would add 60 and 40 together. That'd be 100, and then I'd divide by 2. That would tell me the measurement of the angle on the inside. Okay, so again, kind of the punchline here for angles on the inside of a circle, it's basically taking the average arc length of the two that are created by that angle. It just they're going to be completely side by side across from each other. So for instance, for angle 1, there's going to be the obvious intercepted arc and then the one behind it. For angle 2, there's going to be the obvious intercepted arc that makes that angle, but then there's going to be the one behind it. Add the two front and behind together, divide by 2, that gives you your internal angle. Great. All right, so we talked about this one. This one's straightforward. Just take half of the intercepted arc. There's only one arc to worry about if the angle's on the circle. In this case, now I have two arcs that are created. I'm just taking the average of those two. Now, in this case, what happens if the angle's completely outside of the circle? This will be the last term we talk about in this clip. Scroll this up a bit. All right, so what happens if the angle is outside of the circle? And that can look a couple different ways, and I demonstrate each right here. Okay, just to kind of name these lines, AB right here would be what we call a secant. It passes all the way through the circle at 2 different points. And then line C right here would be a tangent. It only intersects the circle at 1 point. In this second case, I get 2 tangent lines. And in this case, I end up with 2 secants. But in either case, what I end up with fundamentally is an angle outside of the circle. So let me jump to the punchline. Again, you'll notice that this looks very, very similar to the last theorem. For instance, for this guy right here on the left, for angle 1, notice a couple things. First off, that I have 2 arcs that are inside of that Pac-Man mouth now. They both happen to be on the inside, whereas with the inside angle, one was in front and one was behind it. So I'm still taking half of some interaction between those 2 arcs, but here's the punchline. Take the bigger arc, the one that will be further away from the angle, subtract the measure of the smaller arc, the one that's closer to the angle, and then take half of that. The formula is almost exactly the same as previous. It's just that instead of addition, I'm subtracting. So for angles inside the circle, up top here, I would add the 2 arcs together and divide by 2, thus taking an average. Whereas in this case, I'm subtracting the 2 and then dividing by 2. And it will always be the bigger arc minus the smaller arc. If you ever get a negative number on the parentheses there, you just went the wrong direction. Just get rid of the negative and you can keep working. But those are the three theorems.